So the conjugation property basically tells you that the Fourier transform of the conjugate of the original signal, time domain signal, equals to the conjugation of the Fourier transform of the original signal folded in frequency, right? So basically that's what you're telling, what this formula is telling us. So if you conjugate the input signal in time domain, then the Fourier transform in the Fourier domain, you're basically conjugating the Fourier transform also, and then folding it, right? There's a folding operation involved. So that's basically what conjugation is telling us. So now let's look at another property that's called folding. So this is the effect of conjugating the time domain signal, and what's going to happen in the Fourier domain. Here it's folding the sequence in the time domain, and what's going to happen in the frequency domain, right? Let's look at the properties. This particular property. So the Fourier transform of x minus n, the folded input signal, equals to, again, we are using the Fourier transform formula, but the input sequence is no longer xn, it's x minus n now. You see, it's x minus n. So if you compare with the Fourier transform formula, what was the Fourier transform formula? Right, that's the Fourier transform formula, right? xn, that's the input sequence, e to the minus j omega n, and then sum over n, right? But now the input signal is no longer xn. The input signal is x minus n. It's the folded x. So you can sort of see now the input signal is x minus n, and then the rest of the formula is exactly the same, e to the minus j omega n. N goes from minus infinity to positive infinity, a summation, right? And that's going to be the formula we'll have to compute. And the first thing we're going to do is to replace minus n with another variable. It's called n prime. Right, so minus n is replaced with n prime here. You see? And then minus n on the exponent is replaced with n prime also. And then the summation index n is replaced with n prime. Right? And n prime also goes from minus infinity to positive infinity, because so n prime equals to minus n, and n goes from minus infinity to positive infinity, right? And now we can rewrite this formula. We can rewrite this formula in this particular way. Basically, what I have done is that I conjugated the stuff that's inside of this summation, and then I added one more conjugation outside of the summation. So if you actually carry this conjugation, this star, into the summation and the multiplication, you're going to see that the stuff on this, after this equation sign, equal to sign, is actually the same as this thing. So this star is going to cancel this star, right? You get xn prime back. And then this star applied on this exponential function, complex exponential function, is going to cancel out this minus sign, right? And then you get this thing back. So this is actually, and if we actually pay attention to what's the stuff inside of the square bracket, we'll see that it's actually the Fourier transform of x star, the conjugation of x, actually, right? So it's actually, if you don't believe me, it's just it's exactly the same as the Fourier transform formula. There's only one difference. Now the input signal is x star. Of course, n is replaced with n prime, right? But it's it's n prime is just the index. It doesn't really matter. So if you compare this formula with the Fourier transform formula, so we're just looking at this formula, right? You can of course replace n with n prime, right? And then the input signal is replaced with x star instead of x, right? So it's actually the Fourier transform of x star, the stuff that's in the square bracket. Right. The whole thing inside of the square bracket is actually the Fourier transform of x star. And we know the Fourier transform of x star is from the previous property, which is the conjugation property. The Fourier transform of x star equals to big X star e to the minus j omega. You see? So if you actually consider the previous property, the conjugation property, then you can replace big F x star n with big X star e to the minus j omega n. And then if you actually put the star, carry the star into the inside of the square bracket, this star is going to cancel out this star. What you are getting is big X e to the minus j omega. And that's what we want. Big X e to the minus j omega. Right. And let's consider a special case when X is actually a real signal, right? So if X is actually a real signal, then let's go back to this formula, right? Let's go back to this formula. Because X is real, so X star actually equals to X, right? So basically this term becomes this term. So you can basically remove the star from here. You see? You can just get rid of the star because X is real, right? The input signal is a real signal, right? And then the stuff that's inside of the square bracket becomes exactly the same as the equation of Fourier transform, right? Xn e to the minus j omega n sum over n. That's exactly big X e to the j omega, right? And then now you consider the star, the conjugation. You can put the star onto big X. What you are getting is big X star e to the j omega, right? So if the input signal is actually real, then folding it in the time domain is going to conjugate the Fourier transform in the Fourier domain. To see what's actually the implication. So if you actually fold the time domain signal, in principle, you're actually conjugating the frequency domain signal, right? So the Fourier transform of the folded signal, if the signal is real, is equal to the conjugation of the original Fourier transform, right? So now let's look at the Matlab validation, right? Now let's try to understand the folding operation. So here I have constructed a time domain signal. It's a real signal. It's a random with just 5 numbers. And the horizontal axis goes from -1 to 3, and the x is just a normalized Gaussian random signal with 5 sticks. Right. That's my original time domain signal. Now I want to fold the time domain signal. So here I'm calling sig fold. I fold the time domain signal with x and nx as the input, and then the folded signal, the time reversed signal, is stored in x1 and nx1. So that's gonna be my time domain signal and my folded signal. So let's look at what they look like, right? So here's a subplot. That's the time domain signal. nxx. Let's just evaluate this code. So that's my time domain signal. X. So the horizontal axis goes from -1 to 3, right? -1 to 3, and then amplitude is just 5 random numbers, right? And then let's also plot the folded signal, which is nx1 x1. That's nx1 x1, right? That's the folded signal. So that's the folded signal. Right. You can sort of see there are actually the folded signal is symmetric to the original signal with respect to x equal to 0. See, right? And once we have these two time domain signals, we can try to compute their Fourier transforms. So again, we are using this kind of discretization of the frequency axis. So W is actually omega, right? Big M 500. We are using like 500 samples or 501 samples, right? And the range goes from like -pi to pi, I think, right? So it's actually 1001 samples, I think. So because k goes from minus big M to big M, and then W equals to pi divided by big M times k. So when k equals to minus big M, W equals to minus pi, right? And then when k equals to big M, W equals to positive pi, right? So the frequency actually goes from minus pi to pi. And then we can just use our Fourier transform formula that we have always been using, right? This is just one line. This one line Fourier transform, right? So that's the time domain signal multiply this complex exponential, right? But it's a matrix, right? It's a matrix because it's dot hat nx prime. That's transpose of nx times x. It's this formula is exactly the same as what we have used in previous examples, right? We're using the same formula here, right? So right. So that's the Fourier transform of the original signal before folding, before you did the folding, right? Which is x, right? And nx. Now let's compute the Fourier transform of the folded signal, right? All we have to do is to replace x with x1 because x1 is a folded x, and then nx1 is the horizontal axis of x1, the folded x, right? That's all we have to change. And then the Fourier transform of the folded signal is stored in big x1. See, right? So what this equation is actually telling us when x is actually a real signal is telling us that the Fourier transform of the folded signal should equal to the conjugate of the original Fourier transform before you actually folded the time domain signal, right? So all we have to do is to compare the Fourier transform big X and x1, see if x1 is the conjugate of x. So if x1 is the conjugate of x, then the real part should be identical, right? And then the imaginary part should differ by just a minus sign, right? And let's see if it's indeed true, right? If it's indeed true, let's plot the real part first. So here I'm actually plotting the horizontal axis is normalized from -1 to +1, I think, and then I'm plotting the real real part of big X in black, and then the real part of x1 in dash red, and then let's just plot it. So that's the real part. You can sort of see the real part is actually a symmetric function, right? Symmetric with respect to frequency equal to 0, right? And then range goes from -1 to +1. That's the real part. You can sort of see they are indeed identical because the red dash line is right on top of the black solid line, right? Don't see any differences. And then let's just look at the imaginary part. See if the imaginary part happens to differ just by minus sign, right? Again, I'm plotting the imaginary part of big X with black, and then the minus imaginary part of x1 in red dash. So if those two are identical, then red dash line should be right on top of black line, which means that the imaginary part of big X equals to the minus imaginary part of big X1, right? And then that's proving this thing, right? Because it's the conjugation. Conjugation just means the imaginary part differs by a minus sign, and the real part is exactly the same, right? And then let's get back to look at. And then the imaginary part is indeed identical, right? There's no difference. And you can also see it's actually anti-symmetric, right? Because zero frequency is right in the middle, right? It's anti-symmetric, you see. So that's folding, right? So if you actually fold a real signal in the time domain, what you are getting is a conjugation in the frequency domain. So folding in time domain is equivalent to conjugation in frequency domain for real signals, right? And if we consider the previous example, conjugation in time domain involves a folding in the frequency domain, you see. Involves the folding in frequency domain. There's folding here, right? Because it's instead of e to the j omega, you are doing a e to the minus j omega. So folding and the conjugation folding in time domain corresponding to conjugation in frequency domain, and conjugation in time domain involves a folding in frequency domain. You see. So these two operations are kind of related, right? Now let's look at probably the most important properties of Fourier transform, which is the convolution property, which basically tells you that the Fourier transform of the convolution of two signals equals to the Fourier transform of the first signal, big X1, multiply the Fourier transform of the second signal, X2, big X2. Right, so if the input is the convolution of two signals, then the output of the Fourier transform is the Fourier transform of the first signal multiplied the Fourier transform of the second signal. Right, that's probably the most important property of Fourier transform actually, and you probably just have to remember it. But let's still try to sort of prove it. Let's try to prove it. So the convolution of two signals x1 and x2. Let's use the convolution formula, which is the summation x1k, x2 n subtract k. Right, you can think of x1 as the input signal and x2 as the impulse response h, like what we did in previous convolution formulas, right? Or you can think of it the other way around. X1 is the impulse response and x2 is the input signal, right? And that's sort of the convolution formula that we have always been using. Summation over k. Suppose we consider x1 as the input signal and x2 as the impulse response, right? A summation of k. K becomes the parameter that indicates the amount of shift, right? So if x2 is the impulse response, you are basically shifting the impulse response by different amounts, k, right? And then multiplying with the amplitude at the kth shift, right, of the input signal, right? And then do a superposition over k, summation over k. So now we are doing a Fourier transform of this whole summation formula, right? Of the whole thing that's inside the square bracket. We are doing the Fourier transform of this thing, right? We have to sort of take this thing into the Fourier transform formula, right? Basically that's a summation over n, right? And then e to the minus j omega n. Now the input signal is the summation over k here. That's the input signal, the whole thing that's inside of the square bracket, right? Summation over k. That's a convolution, right? So you basically have to stick the whole thing into the Fourier transform formula and use that as the input signal now, right? And now let's look re-examine the whole thing, the whole formula, right? So x1k depends upon only k. x2 n subtract k depends upon n and also on k, right? And then e to the minus j omega n depends upon only n. It doesn't depend on k. And this summation over n doesn't depend on k, right? So let's try to collect all the terms that involves n, right? So summation over k, x1k, it doesn't depend on n, right? So let's just move it outside. And then we can just switch the order of summation, these two summations, right? We carry out the summation over n first, and then it's x2 depends upon n, so x2 n subtract k e to the minus j omega n, right? You can sort of see what's actually the stuff that's inside the square bracket, right? It's the Fourier transform of a shifted x2, and the amount of shift is exactly k, right? So it's a Fourier transform of a shifted signal, and the amount of shift is by k. So now we can actually use our first time shifting property. So that's the time shifting property, right? The Fourier transform of a shifted signal equals to the Fourier transform of the original signal times e to the minus j omega k. K is the amount of shift, right? So now we can use this time shifting property and to write out the stuff that's inside of this square bracket, because it's a Fourier transform of a shifted x2. The Fourier transform of shifted x2 equals to the big x2 e to the j omega times e to the minus j omega the amount of shift k, right? And we are using the time shifting property of Fourier transform here, right? So the stuff that's under the selection is the Fourier transform of x2 and subtract k, the shifted x2. Right. Big x2 is a function of omega. It doesn't depend on does not depend upon k or n, right? It's a function of omega. But e to the minus j omega k depends upon k here. You see? And then you have a summation over k here, and then x1 depends upon k, right? And then let's just look at the whole formula under the selection. And it happens to be the Fourier transform of x1. If you replace k with another index, say n, then it becomes x1n e to the minus j omega n sum over n. And that's exactly the same formula as the Fourier transform of x1. So the whole thing that's under the selection is big x1 e to the j omega. So that's actually is proving this formula is correct, right? The Fourier transform of two signals convolving together equals to the Fourier transform of the first signal multiplied with the Fourier transform of the second signal, right? So again, let's look at the Matlab validation of this process, right? So let's try to construct the two signals first. So nx1 goes from -1 to 3. That's the horizontal axis of the first signal. And x1 is just a random number, five random numbers. x1, that's our first signal, x1. And its horizontal axis. And then that's our second signal, nx2, goes from -3 to 2. And then it's 6 random numbers. That's x2. Right. Of course, we have to convolve them together. We are using our own convolution code, conv_m. Right. x1, nx1, x2, nx2. And the output of the convolution is put into x3, nx3. So x3 and x3 is going to hold the convolution result of this thing under the selection. So the convolution of x1 and x2, that's stored in x3 and x3. Right. So let's look at these three signals, right? So let me open a new plot. So here I'm actually making 5 subplots. The first one is going to be the first signal in time domain, x1, x1. Right. Let's make a plot of it. That's the first signal. So that's going to be our first signal, right? Some random numbers. And then that's our second signal. Our second signal. So it goes from -3 to 2. -3 to 2. The first signal goes from -1 to 3, I think, right? And then the third signal is the convolution of the first and the second signal. That's a convolution of these two signals. The first signal, the second signal. The third signal is a convolution of these two. Right. And now let's do the Fourier transforms. Again, we are using the same horizontal axis in the frequency domain. So big M equals to 500. Small k goes from minus big M to positive big M, and then frequency omega is W here, goes from -pi to positive pi. Right. Again, we are using our one line Fourier transform formula. That's the Fourier transform of the first signal, x1 and x1. Right. And then that's the Fourier transform of the second signal. You see, x2 and x2. And then that's the Fourier transform of the third signal, x3 and x3. And the Fourier transform of the third signal is what? Is actually the third signal is the convolution of the first two signals. Right, it's the convolution of the first two signals here. So basically big X3 is the Fourier transform of x1 and x2 convolved together. So big X3 is the Fourier transform of the convolution of x1 and x2. Right. So big X3 is basically the left-hand side, right? And then the right-hand side is what? The right-hand side is the Fourier transform of the first signal multiply the Fourier transform of the second signal, right? So we have the Fourier transform of the first signal that's stored in big X1. And then we also have the Fourier transform of the second signal that's stored in big X2. And then because both signals are in the same horizontal axis, which is W, okay, right? The same horizontal. So if I want to multiply these two signals together, I can just do a dot multiply, right? And of course, I can also use my own sigma out, right? But there's no need because the horizontal axis for both signals are identical, right? So I can just dot multiply these two signals together. That's going to be XX3. And XX3 is going to be the right-hand side. That's basically the Fourier transform of the first two signals multiplying that together. Right. And then we have to validate if the left-hand side is exactly the same as the right-hand side. So we're going to compare the real part and also the imaginary part. So here I'm comparing the real part. That's the fourth subplot. The horizontal axis is the frequency, normalized frequency, goes from -1 to positive 1. And then the real part of X3, real part of the X3 is basically the real part of the left-hand side, right? And then that's plotted in black. And then I'm plotting the real part of XX3, which is basically the real part of the right-hand side. And that's in red dash, right? If they are identical, the red dash should be right on top of the black solid line, right? Let's just execute this part. And you can sort of see it's exactly the same, right? There's no difference. And now we have to compare the imaginary part also, right? That's in the fifth subplot. Again, we're plotting the normalized horizontal axis is the normalized frequency, and then that's the imaginary part of big X3. That's the imaginary part of left-hand side. It's plotted in black, right? And then that's the imaginary part of XX3. That's the imaginary part of the right-hand side, and it's plotted in right dash, right? And then let's just plot it. And again, you can sort of see they are identical, right? Identical, exactly the same. So it's basically telling you that the convolution, the Fourier transform of the convolution of two signals equals to the Fourier transform of the first signal multiply the Fourier transform of the second signal. Do you see? Right. That's convolving two signals, right? Now suppose you want to convolve three signals. X1 convolve X2 convolve X3 and then Fourier transform. Right? Can you guys imagine what's going to be the output, right? I can tell you the output is going to be big X1 times big X2 times big X3, right? So that's so in time domain, if you convolve multiple signals together, in frequency domain, it's equivalent to multiplying the Fourier transforms of each of the individual signals, right? And because of laws of commutation, association applies to convolution in time domain, right? You can sort of see why you have that kind of commutation and association properties for convolution, right? Because commutation and association properties apply to multiplications, right? And the multiplication in frequency domain is exactly the same as convolution in the time domain. It corresponds to so whatever sort of laws applicable to multiplication is applicable to convolution in time domain, right? Multiplication in frequency domain has the commutation property and also has the association property and also has the distribution property if you sort of consider the summation or subtraction, that kind of thing, right? So convolution also has all those properties. The reason is because convolution in time domain is equivalent to multiplication in the frequency domain. It's equivalent. It's equivalent, right? And we have proved that. And this particular formula actually gives us a different way for computing convolution, right? If you think about it, because what you can do is to, if you want to get the convolution of two signals, what you can do is to convert the first signal to the frequency domain, and also convert the second signal to the frequency domain, and then you can just do a multiplication, right? You can do a multiplication, and then convert the result of the multiplication back to the time domain by doing an inverse Fourier transform, right? So that actually gives us another way of computing convolution. Instead of just computing convolution in the time domain using that summation formula, sum over k, that kind of thing, using this kind of formula, right? You have a second way of doing convolution now, right? You can convert the first signal to the frequency domain, convert the second signal to the frequency domain, multiplying them together, and then convert it back to time domain using an inverse Fourier transform, right? And in practice, many people do that because the efficiency of Fourier transform is actually very high on modern computers. Actually, it's very fast, right? So this summation formula can involve lots of multiplications and also summations, right? Those are actually lots of calculations if the two signals are very long, right? Very long signals. If you have very long signals, computing this summation and also the multiplication is gonna consume a lot of computing power, right? But FFT is very fast. So if you use FFT, you can just do a Fourier transform, and in frequency domain, it just involves a dot multiply because it's a element-wise multiplication. Just multiply the corresponding elements together, right? And then you can do a inverse Fourier transform, which is also very fast. So this Fourier domain calculation of convolution becomes more efficient, especially when the two signals are long, right? And in practice, people often do that. If the two signals are very long signals, then you do a Fourier transform first, and then do a multiplication in the frequency domain, and then convert the result back to time domain using inverse Fourier transform, which is far more efficient, which can be far more efficient than doing the convolution in the time domain, right? And this kind of efficiency gain becomes more and more obvious if the two signals are longer and longer, right? For very long signals, convolution calculation in frequency domain is more efficient. Now let's look at another property that's closely related to the convolution property. Right, here we have convolution for a transform of the convolution of two signals equals to the Fourier transform of the first signal multiplied the Fourier transform of the second signal. Here we look at the correlation, right? And then the Fourier transform of x1 correlating with x2 equals to the Fourier transform of the first signal multiplied with the conjugation of the Fourier transform of the second signal. So in lesson 2, what we talked about, one of the results what we got in lesson 2 was that correlation is convolution after folding one of the signals, actually, right? And you guys can imagine why we have a complex conjugation here, because of folding, right? So if you actually fold one of the signals, that's the folding property, right? If you fold one of the signals in the time domain, you're going to get a conjugation in the frequency domain. You see? So folding is equivalent to conjugation in the folding in the time domain is equivalent to conjugation in the frequency domain. Well, we talked about correlation in lesson 2, and what I was telling you is that correlation is basically convolution after folding. You have to fold one of the signals before doing the convolution, right? So convolution means multiplication, right, in frequency domain. Folding means you have to conjugate one of them. Here we're actually conjugating the second signal here. Right. So let's look at how we actually got this result, right? So the Fourier transform of two signals correlating with each other. So here we are actually using the correlation formula in the time domain. A summation over k and x1k times x2k subtract n. You can sort of see the difference here, right? The difference with the convolution formula that we are using, right? In the convolution formula, it's x1k, x2, n subtract k, sum over k, right? Here it's x1k, x2k subtract n, sum over k. You see? Different. So, but the technique we're gonna use is quite similar, right? We basically bring the whole summation, the stuff that's inside the square bracket, into the Fourier transform formula, which is e to the minus j omega n, sum over n. Right? We take the whole thing inside of the square bracket and then put it into the location of the input signal. Now the input signal is not xn anymore, it's the whole thing inside of the square bracket, right? Again, x1k doesn't depend upon x1k, and this summation over k doesn't depend upon n, so we can take this thing out and then switch the order of the summation over n and the summation over k. So here it's summation over n, and then x2 k subtract n e to the minus j omega n, right? And at this point we can first of all, you can sort of see it's the input signal now, it's actually a shifted folded x2, right? Because there's a minus sign in front of the n. You see? Right? So it's actually a folded x2, and then it's also being shifted by k. Right? So we can use previous properties. Folding property, it's going to give you the conjugation, and then shifting property, it's going to give you e to the j omega minus j omega k this time, right? We can use those two previous properties that we have talked about, a shifting property and then a folding property, right? But let's still try to carry out the calculation in the normal way. Let's try to replace k subtract n with another index. Let's just call it n prime, right? So n prime equals to k subtract n. So n equals to k subtract n prime. So here n is replaced with k subtract n prime. And then the summation index becomes n prime. N prime also goes from minus infinity to positive infinity, right? And now we can take out e to the minus j omega k out of the summation, because the summation is over n prime, and e to the minus j omega k doesn't depend upon n prime, so we can take that thing out of the summation n prime, right? And then what's actually left inside of the summation becomes summation over n prime x2 n prime, and then e to the j omega n prime, positive j omega n prime, because this minus sign, and this minus sign is going to cancel out, right? And we can rewrite that formula in this particular way, right? So if you actually put this conjugation, this star, into the summation, this star and this star is going to cancel out. It becomes x2 n prime, right? And then this star is going to change the sign of this e to the minus j omega n prime. It's going to turn it into e to the positive j omega n prime, right? And that's e to the positive j omega n prime, because this minus sign cancels out, right? And if x2 n prime is actually real, which is often the case, right? Usually you are dealing with time domain real signals. In time domain, you are not really dealing with complex signals, right? So if x2 n prime is actually real, then x2 star n prime equals to x2 n prime, right? Because x2 is real, right? So you can get rid of this star, get rid of this particular star, right? If x2 is real. And then the stuff that's inside the square bracket becomes the Fourier transform of x2, right? So the stuff inside of the square bracket becomes big x2, and then you cannot forget about this star, this conjugation. You have to move that conjugation onto this big x2, right? And then you can just examine this part under selection, it happens to be the Fourier transform of x1. You see, it's x1k e to the minus j omega k sum over k. If you just replace k with n, right, you recover the Fourier transform formula. Right, so the whole thing that's under the selection becomes big x1 e to the j omega. Right. So that's why you have this equality. So the Fourier transform of the correlation of two signals equals to the Fourier transform of the first signal multiplied with the conjugation of the Fourier transform of the second signal. Right. So because of this conjugation, it makes the correlation not commutative. You see, if you actually do Fourier transform of x2 correlating with x1, and then the conjugation is going to be applied on big x1 instead of big x2, right? Because you're actually correlating x2 with x. So Fourier transform x2 correlating with x1, right? So then the conjugation is going to be applied on the x1, big x1. So it's not commutative. Right. But now let's look at how we can actually validate this formula in Matlab. Right. So here I'm still constructing two signals, x1, x1. That's the first random signal, and the range goes from -1 to 3, right? And then that's the second random signal, goes from -3 to 2. The range is exactly the same as before, but the random numbers could be different from the convolution example that we did already. And then x3 and x3 now becomes the correlation of x1 x1 and x2 and x2. So here I'm actually using our own correlation formula, a correlation routine. It's xur underscore m. And that's the body of xur underscore m. That's the function, how we actually define this thing. And in this function, we talked about this function in lesson 1, right? We did some experiments with this particular function. Right? Here I'm actually, you have two input signals, xy, right? X and x, y and y. Here I'm actually folding the second signal, y and y, before actually doing a convolution. So conv underscore m is our own convolution routine. What I was telling you, correlation in time domain, correlation is basically convolution after folding. Right, here I'm actually folding the second signal and then doing a convolution. It's a time domain convolution routine. Right. And the convolution is between x, the first signal, with the folded second signal. Y and y is the folded second signal. Right. So the result of the correlation is stored in x3 and x3. Right. And then we do our Fourier transform. That's the frequency axis. Big x1 is the Fourier transform of x1 and x1. Big x2 is the Fourier transform of x2 and x2. And then big x3 is the Fourier transform of x3 and x3. And x3 and x3 is the correlation of x1 and x2 in time domain. Right. So big x3 is basically what? Big x3 is the left-hand side. It's a Fourier transform of these two signals correlating together. That's the left-hand side. So x3, big x3 is the left-hand side. Right. And then let's try to construct the right-hand side. The right-hand side is the Fourier transform of the first signal multiply with the conjugation of the Fourier transform of the second signal, right? So the Fourier transform of the first signal is big x1. That's big x1. Multiply. It's a component-wise multiply, so it's a dot multiply. The conjugation of big x2. So Matlab conjugation function, CONJ, that's the Matlab conjugation function. You apply the conjugation function element-wise on big x2. That's the Fourier transform of the second signal. And then big x3 is going to be the right-hand side. Right. So basically we have to compare the big x3 with big x3. We have to compare these two, right? and see if they are identical. So, but let's look at the time domain signal first. That's the first signal in time domain, right? It's from -1 to 3, I think, right? And then that's the second signal in time domain. That's the second signal from -3 to 2, right? And then let's look at the correlation of these two. That's x3 and x3. That's the correlation between between these two signals. That's the correlation, right? So it looks like the last stick comes to 6. So is that true? If you flipped it, right? The last stick goes to 3, I think, right? Because it's a -2, 3, right? -2 to 3. 3 plus 3, that's 6, right? So that's the last stick. So that's our time domain signals. That's our time domain signals. Now let's look at the frequency domain signals. So on the fourth subplot, I'm plotting basically the real part of the left-hand side, which is stored in big X3, the left-hand side. That's the Fourier transform of the correlation, big X3. That's the real part of the left-hand side, plotted in black. And then I'm plotting the real part of the right-hand side. That's XX3, and it's in red dash. You see? So that's the real part. Let's just run it. That's the real part. And you can sort of see they are exactly the same. Right? And then let's compare the imaginary part. So on the fifth subplot, I'm plotting the imaginary part of the left-hand side, which is big X3, right? In black. And then I'm plotting the imaginary part of the right-hand side. The whole thing. The imaginary part. Big XX3. In red dash. Again, they are exactly the same. Right? So we have validated the correlation result. Right? The correlation property of DTFT. So this formula basically gives you a second way for computing correlation also. Right? Just like convolution, you can do it in the frequency domain. You can do correlation in the frequency domain also. Right? So all you have to do is to convert the first signal into the frequency domain. You get big X1. And then convert the second signal into the frequency domain also. You get big X2. And then all you have to do is to conjugate the second signal, big X2. Which is a very simple calculation, just to flip the sign of the imaginary part of X2, big X2 basically. And then you do a element-wise multiplication. Once you get the result, you do an inverse Fourier transform to the time domain, and then what you are getting is a correlation. Right? So this kind of a Fourier domain correlation calculation becomes more and more efficient if x1 and x2 is very long, becomes longer in the time domain. Then the calculation in the frequency domain becomes extremely efficient, because the Fourier transform and its inverse Fourier transform is very efficient on modern computers, right? So it actually gives you a second way for doing correlation, right, in the Fourier domain. So we have talked about the convolution and the correlation, and how you can actually do convolution and correlation in the Fourier domain, in the frequency domain, basically. If your horizontal axis is time, then so correlation in frequency domain, correlation is equivalent to the Fourier transform of the first signal multiply the conjugation of the Fourier transform of the second signal, right? And then for convolution in the Fourier domain, it's equals to the Fourier transform of the first signal multiply with the Fourier transform of the second signal. Right, that's convolution and correlation in the Fourier domain. And now let's look at another property, that's multiplication. So if the Fourier transform of a convolution equals to multiplication in the Fourier domain, then what's the Fourier transform of multiplication in time domain, right? So here it's actually we are just multiplying two signals together, right? And then we're doing a Fourier transform of the product of these two signals, right? And you can actually prove that the Fourier transform of multiplication actually equals to convolution in the frequency domain. So it equals to the Fourier transform of the first signal convolve the Fourier transform of the second signal, right? So you can sort of see the symmetry here, right? So multiplication in frequency domain is equivalent to convolution in time domain, and here convolution in time multiplication in time domain is equivalent to convolution in frequency domain, right? So that's, you can sort of see some symmetry in the Fourier transform, right? So how do we actually prove that? Convolution. So here omega is actually treated, so x1 and x2 are frequencies, are functions of frequency omega, right? But for now, we are actually treating omega as some kind of a continuous variable, right? We are not really treating it as a discrete variable like n. We're treating it as continuous variable omega, right? So if you do the convolution, then you have to use not the summation, but using an integral here. So here, because x1 and x2 are functions of a continuous function, are functions of a continuous omega. So now you have to sort of replace summation with the integral. Here we are using, if you are using a summation, then you have two indices, right? One is omega, then the other one is what we call Cassi, for example, right? And then you do a summation over Cassi, for example, right? Yeah. If you compare this formula with the convolution formula that we were using before, it's like that. No, it's like this kind of thing, right? It's a summation over a k, the parameter k, and then the first variable is a function of k, right? And then the second variable is a function of n subtract k, right? Suppose you replace k with Cassi, so it's and replace small x with big X, then it's big X1 Cassi times big X2 and no, not m anymore, but omega subtract Cassi, and then you integrate over Cassi instead of sum over k, right? So that's sort of the continuous form of convolution. So Cassi, omega subtract Cassi, and then integrate over Cassi, right? And then what exactly is x1 Cassi, right? X1 Cassi is the Fourier transform of the time domain signal x1. But now instead of using omega, we are using Cassi to denote the frequency here, right? So basically you can replace big X1 Cassi with this summation, which is basically the Fourier transform with the frequency parameter omega replaced with Cassi, right? But it doesn't really matter because you can use any symbol to denote frequency. Here we are using Cassi to denote frequency, right? And then this is essentially the Fourier transform of x1 in time domain. And then this is the Fourier transform of x2, but with omega subtract Cassi as the frequency variable. So here it's again the Fourier transform formula with x2, and then we use a different index n prime, right? It's because there's no reason for this summation index n to be exactly the same as this summation index n, right? So we use a different summation index n prime in the Fourier summation, in the Fourier transform. So n prime, sum over n prime, and then the frequency, instead of using omega, you are using a different variable, omega subtract Cassi. You see, and then we can rearrange the order of the summation and the integration, right? So because this integral is over Cassi, right? And the terms that contains Cassi is basically this term and then this term, right? So we can just move all the summations together, n prime n, x1 n, x2 n prime, and collect these two exponentials, right? So e to the minus j Cassi n, e to the minus j omega subtract Cassi n prime, right? And e to the minus j omega n prime actually does not depend upon Cassi, so we can take it out of the integral. So that's e to the minus j omega n prime. It doesn't depend on upon n c, and then we can collect the terms that contains the c. Then what we have is e to the minus j c and subtract n prime, and then integrate it over c. Now we have to use a different. We have used a result. This integral, if you Google about it, this integral actually gives you a result that's the direct delta function and subtract n prime. So it's an impulse that has been shifted by n prime, and then you have a summation over n prime, right? So which means over the summation of all the possible n prime, there's only one value that actually has contribution, right? Which is at n prime equals to n. So in this case, you can replace n prime with n. So summation over n, x1n, x2n. Replace n prime with n. And then e to the minus j omega n prime, replace n prime with n, you get e to the minus j omega n. And if you look at this particular formula, that's exactly the Fourier transform of x1n times x2n. Right? So this is a quite rough sketch about how you can actually make a proof of this particular equation, right? And in practice, one thing that you have to sort out is this particular integral. What does it equal to, right? You can think about it, right? You can, if you sort of expand this thing into cosine, subtract I sine, expand Euler's form into using the Euler's formula, cosine subtract I sine thing. Sine is actually a anti-symmetric function, right? Integral over it is going to give you exactly 0, but cosine is actually a even function. So the integral of this thing is going to give you something we call a sinc function, and then you can take the limit of the sinc function, and eventually it's going to give you a direct delta function, right? And another thing is that this summation over n prime, right? This is not exactly correct yet, because the direct delta function works. The shifting property of the direct delta function works when you do an integral over n prime, right? So you have to sort out that particular issue here, right? But in general, that's sort of the general idea of how you can actually get a proof of this result. So multiplication in the time domain is actually equivalent to convolution in the frequency domain, right? It's just like the symmetry of this property. So convolution in the time domain is equivalent to multiplication in the frequency domain, right? So I'm gonna skip the Matlab validation for the multiplication property, right? You guys can give it a try if you are interested, right? But you have to be careful about how the convolution is implemented. And now let's look at the last property that I'm going to talk about. It's called the energy property, Parseval's theorem. What this theorem is basically telling you is that so here it's actually a summation of the square of the amplitude of the signal in the time domain, which basically gives you the energy in the time domain, how you actually compute the energy, right? That's how you compute the energy, right? You just square the amplitude at every time sample and then sum them together. Then what you get is the energy. And this energy actually equals to the integral. Here we are treating omega as a continuous variable, so it's an integral. And then you square the the amplitude, because the big X is a complex number, right? But if you take the absolute value, you are getting the length of the complex vector, right? It's basically it's telling you for every complex number you have a length, right? If you look at the complex plane, real part in the horizontal axis, imaginary part on the vertical axis, and the complex number is just a point in that complex plane. And that point, the distance between that point and the origin is basically the length of that complex number, right? And a big X is just a complex sequence, right? So inside of this big X vector, every element is a complex number. So every element is going to have a length, right? So taking the absolute value is going to give you the length of every element inside of this big X complex sequence, right? And then you are squaring, taking a square of the length. And then you integrate over minus pi over pi, because omega has a range from minus pi to pi, right? And then you divide the integral by 2 pi. That's basically the length of the interval, right? So basically that gives you another formula for computing the energy of a signal, right? You can compute it either in the time domain or in the frequency domain, and both numbers are supposed to be exactly the same, right? That's called Parseval's theorem, right? And let's just do a Matlab validation of this result. Let's do a Matlab validation of this result. So here I'm defining a random variable x, random sequence, and x goes from -1 to 3, right? X is a random sequence that has like a 1 row 5 columns, right? 5 numbers. And then the left hand side, the time domain energy, can be computed by just doing a summation of x dot hat square, right? It's element wise square, and then you do a summation of it. Then what you're getting is the time domain calculation of the energy, right? Time domain estimate of the energy. Now we have to compute the Fourier transform first in order to get the big X, right? Again, I'm using the same frequency axis, but with just fewer samples. Big M is 100, and then small k goes from minus big M to big M, and then omega, that's W here, is pi divided by big M times k, so it goes from minus pi to pi, right? And then if I want to do my Fourier transform, I just use this one line formula. Big X equals to small x, this whole thing, and then now I've got my big X. Now I have to do an integral from minus pi to pi. Big X has a horizontal axis that goes from minus pi to pi, right? So how do I do this integral, right? And Matlab has a function, it's called traps. It's actually using the trapezoidal rule to do a numerical integration. So if you haven't used this particular function before, you can type help trapz. It's basically telling you how you can actually carry out a numerical integration. So traps y computes an approximation of the integral of y via the trapezoidal method with unit spacing. So it's actually assuming the horizontal spacing is 1. In our case, the horizontal spacing is not 1, right? In our case, the horizontal spacing is actually given by that, right? That's our frequency axis, right? That's our frequency axis, that's horizontal axis for big X. So the interval is actually pi divided by big M. It's not 1, right? It's pi divided by big M, right? So if we want to use the Matlab function for carrying out this integral, we can call trapz. And then the function that needs to be integrated is the absolute value squared. So it's the absolute value of big X dot hat 2 element wise squared. That's gonna be our integrand, right? And then because traps is assuming the horizontal axis is 1, but the horizontal unit is not 1. It's a pi divided by big M. So we need to multiply pi divided by big M, which is basically d omega here. So trapz is basically giving you this integral with d omega assumed to be 1, but now d omega is not 1. D omega is pi divided by big M, so we need to multiply pi divided by big M, right? So this whole thing is gonna give you an approximation to this whole integral, and then we divide by 2 pi, right? That's our E2. That's our frequency domain estimate of the energy of the signal, right? And then we can compare them. Energy. We are printing out the energy, E1 and E2, right? So let's just give it a try, right? So if I just run it, so you can see they are basically identical. So energy in the time domain, that's E1 equals 4.8635, and then energy in the frequency domain, 4.8635, exactly the same, right? For the printed out digits, right? So if we want to look at the discrepancies, energy difference num to str. Num to str is another Matlab function, allows you to convert numbers to string characters. So I'm taking the absolute value of the difference, basically. Right. Energy difference is 0, right? So maybe if I want to format long, so here it's gonna print out more of the digits. So energy difference is 2.22 e to the minus 16th power, right? So that means it's actually quite accurate. The difference between these two is very, very small, right? You can, if you reduce the number of samples, it's gonna increase it. So if I change 100 to 50, for some reason it's not really. So now it's 10 to the minus 15th power, right? So it's increasing. The difference is actually increasing. So if I for some reason reduce it depends upon what kind of function it actually is, right? It depends upon this function. So suppose I give it more numbers, for example. Size in x, right? Now the difference becomes quite large, right? But if you actually increase the number of samples in the frequency domain, then it's gonna reduce it, right? 50. Let me give it a try. So 50. It looks like 50 is more than enough. 50. How many points do I have? This is 30. 10 is 40. So if I give it like 40, let me see what's gonna be the result. 30. Okay. So basically that's what we call Parsifal's theorem, right? You can compute the energy either in the time domain by doing a summation of the time domain signal, the square of the time domain signal is the amplitude of the time domain signal square of it, right? And then do a summation. Or you can do a summation in the frequency domain, do an integral in the frequency domain, and then divide it by 2 pi. So basically that's all the properties about the Fourier transform that I wanted to talk about, right? And in the next video, we're going to talk about the consequences of the frequency domain representation in terms of the linear time invariant system, right? And we're going to see some interesting results, and we're also going to look at some properties of the sampling theorem, how we should sample our continuous signal using a discrete sequence, how we should do that kind of sampling in order to actually maintain all the information or keep all the information without introducing any kind of distortion, that kind of thing, right?